we were on enthalpy change of hydration. We made our concept back. We were on enthalpy change of hydration, and we discussed the idea that water is a part of this process, and water is present in case of hydration. Water is a polar molecule. Water is a polar molecule. Now, water is capable, if water is a polar molecule, let's say I draw two water molecules. Here, there is a negative charge on oxygen and there is a positive charge on hydrogen. If I put a sodium ion here, this is a sodium ion. If I put a sodium ion here, and again, if I put two water molecules like this, now you can find a force of attraction here. Sodium will be surrounded by water molecule because sodium is a positive ion and water molecule is a polar molecule. What is the result? What is the result? The result is that ion is surrounded by water molecule. This is called hydration. So what is hydration? Hydration is a process in which an ion is surrounded by water molecule. We use the word infinite. We have used the word infinite dilution. This is a mathematical type of thing that if you a solution is so much diluted, a solution is so much diluted that further change in concentration does not occur. I'm putting my first concept again. What is hydration? An ion is surrounded by water molecules in an aqueous solution. Look, this is sodium and it is surrounded by water molecules. So now write down the first concept for today. Write, you have already written this scheme. So write under it that hydration.
Okay.
Hydration is a process hydration is a process in which an ion is surrounded by water molecules in an aqueous solution. Now, how come water can do this job? How come water is capable of doing this activity that now requires a concept from our O-level, from our AS chemistry? What is the concept? Now you have to write, and I already had explained that water is a polar molecule Water is a polar molecule. I'm drawing my diagram from AS background. And hydrogen is partially positive, yes, and oxygen is partially negative. This is called a polar molecule with a bond angle of 104.5. You have to copy this screen. You have to update the same screen.
Yes.
Okay, so we got this concept back. Okay, this is a permanent link which I have sent you once, and you can always join the same link in every class. So we move to our diagram. Look, sodium positive is surrounded by water molecule. Look at this process. This process is called hydration. Some energy is released in this process, and that energy is called enthalpy change of hydration. So make a concept. What is hydration? When water molecules surround an ion in an aqueous solution, it is called hydration. After this process, some energy is released, and that energy is called enthalpy change of hydration. So these are two concepts in our the two concepts in our class by now. Now, right under it, for example, right under it, for example, and then copy this screen.
Okay. I've copied.
Okay, and we made these two concepts. Now, look at this chlorine. Achha, do you remember that sodium and chlorine, they were very famous in O level because of the compound sodium chloride. In that ionic lattice of sodium chloride, sodium is a relatively smaller ion because of positive ion, and chlorine is a relatively bigger ion. Look at carefully that water molecules are also surrounding chlorine. But this time, but this time, water molecules are using their H poles, HH. Now you have to copy this screen.
Okay.
Note that Cl minus is relatively a bigger ion.
Okay. I've copied.
Water molecule is a polar molecule with a bond angle of 104.5. Sodium ion is surrounded with water molecules. Chlorine ion is also surrounded with water molecules. Now, this is our concept, and the energy involved in this process is called hydration. After copying these two diagrams, write under it that the energy released in this process, the energy released in this process,
Yes.
the energy released in this process is called enthalpy change of hydration. The energy released in this process is called enthalpy change of hydration.
Okay.
Now, we put our third concept for today. Look at this concept, that enthalpy change of hydration. Enthalpy change of hydration is always exothermic because it is a type of bond formation.
Yes.
If you look at this diagram carefully, it is a type of bond formation. It is a type of bond formation. So enthalpy change of hydration is always exothermic. Now, if you move forward, right under it, look at the screen first. Enthalpy change of hydration depends upon charge density. It depends upon the quantity of charge, and it depends upon the, and it also depends upon the size of the charge. Now, I show you some examples. You have to see H plus. You have to see H plus minus 1130. Okay. Now, you look at the number Al plus 3. Look at this value. Huge difference, minus 4,665. So it means aluminum plus 3 has a much higher energy than H plus. Why? Because aluminum has plus 3 charge. Do you remember that as you get positive charge, the ionic size decreases, and as you get negative charge, ionic size increases?
Yes.
Good. Similarly, look at Mg2 plus, very high hydration enthalpy. So our next concept is there that enthalpy change of hydration depends upon charge and depends upon size. Now you have to copy this thing.
Okay. I've copied.
Good. Now, our next concept, which will be our next concept for today, hydration enthalpy becomes less exothermic as we go down the group. Again, I will be needing some backup from AS chemistry. And what is the backup? That if you are going down a group, the size of the atom increases or decreases. Look at the screen. If you are moving down a group, the ionic size increases. When ionic size decreases, charge density decreases. So hydration enthalpy becomes less exothermic because hydration depends upon the charge density, electron cloud density. So if you see, the medium is a much bigger plus. and lithium is a smaller plus. Both are plus 1. Both are plus 1, but lithium plus 1, will be more readily hydrated because of its high charge density. Now you have to copy this screen.
Okay. I've copied.
Okay. Hydration enthalpy becomes less exothermic. This is a typical chemistry language. It actually means that hydration enthalpy decreases down the group. Hydration enthalpy decreases because less exothermic means less energy is released then to hydrate a bigger ion. So it's more energetic to hydrate lithium than potassium because lithium is small and plus 1, while potassium is bigger and the same plus 1. You have to copy this screen.
Okay. I've copied.
Now, give a new heading, process of salvation.
Okay. I've given the heading.
What is solvation? Solvation means making a solution. Solvation means making a solution. It actually means that there are 2 steps in process of solvation. Solvation is a 2-stage process. Number 1, reverse of lattice formation, and number 2, hydration. You have to copy this screen.
Okay. I've copied.
Get this one. Can you tell me what is reverse of lattice formation?
Maybe breaking the bonds between the oppositely charged ions in the lattice.
Can you repeat what is this?
Breaking the ionic bond between the oppositely charged ions if it's Ionic lattice.
This is basically breaking down of lattice. In hydration today we have discussed. So whenever we are willing to make a solution, we should remember we should remember that there are two stages. We first have to break the bond. We first have to break the lattice, and then we have to make the ions solvated, hydrated in an aqueous solution. So there are two stages. There are two stages of solvation. Look at the first stage, and that is the ionic crystal. You first break down the crystal and you separate them in an aqueous solution. You first break the lattice, you first break down the lattice, and then you are supposed to hydrate the ions.
Mm.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution. Sodium chloride crystals are held together by attractive forces between the positively charged.
Let's add a small amount of table salt, sodium chloride, to water. As you know, sodium chloride dissolves in water. Click on the zoom button to view sodium chloride. Polar water molecules interact with the positive and negative ions of a salt. The positive ends of the water molecules are attracted to the negative chloride ions. The negative ends of the water molecules are attracted to the positive sodium ions. This interaction between water and the salt ions causes a salt to break apart or dissolve in water.
When an ionic solid is added to water, the polar ends of water molecules are attracted to ions on the surface of the crystal. Positively charged hydrogen atoms bond to anions, while oxygen atoms bond to cations. This attraction distorts the electron clouds around the ions and loosens the ionic bonding within the crystal lattice. At the same time, water molecules at the surface of the crystal are also attracted by other water molecules via hydrogen bonding. As a result, ions leave the crystal lattice and enter the liquid phase. Each of them is surrounded by a number of water molecules arranged in several layers. When an ionic solid
When water is added, the salt crystals separate into sodium and chloride ions. Each positively charged sodium ion attracts the negative end of some water molecules. At the same time, negatively charged chloride attracts the positive ends of others.
So these are the two stages.
The spheres of hydration that form around the ions keep them suspended in the fluid.
Now, orally, what is enthalpy? What is enthalpy change of neutralization? Neutralization is a concept which is in our O-level also, and it was in our AS also. When an acid and a base react, a salt and water forms. This is called neutralization. There are different reactions. You can see there are different reactions which are showing neutralization, but overall, the equation which we have to learn is this. H plus OH minus gives you H2O. This is called the equation of neutralization. Achha, what is enthalpy change of atomization? Now give a new heading, enthalpy change of atomization.
Okay.
What is atomization? If you break a substance, a molecule, into its individual atoms, suppose you have H2, and you break it in H plus H. You have ozone, and you break it O plus O plus O. If you do that, this is called atomization.
Yes.
Enthalpy change of atomization is the amount of enthalpy change when a compound bonds are broken and the component atoms are separated into single atoms. And this enthalpy change is denoted by delta H atomization. So you have to look at the definition. Now you have to copy this screen. This topic is coming from AS level. We need it here, so we are copying it.
Yes. Okay, I've copied.
Have you copied it?
Yes, no.
Look at these few equations, especially look at the balancing half, not putting 2 on the right side, then half Cl2, not putting 2 on the right side, Na, solid, and Na, gas. These are some equations we call as atomization. You have to copy these examples.
Okay. I copied.
Now, can you recall what was bond enthalpy? Look at the screen. No need to copy it. Just orally recall what is bond enthalpy.
Okay. Okay, I've got it.
So, what is bond enthalpy? It was a concept in AS that when a chemical reaction takes place, older bonds are broken and new bonds are formed. Older bonds are broken and new bonds are formed. So what we used to do, we used to calculate the bond energy from the data booklet and we subtract the difference between enthalpy change of reactants and enthalpy change of products. I want to make a quick recall for that, and this was a topic involving bond energy calculation. Can you recall this reaction?
Yes.
Was it bromination of ethene? Bromination of ethene?
Yes. Halogenation.
If I want you to recall that there was a double bond
Yes.
and there was a single bond.
Yes.
Look at this. This is called bromination of ethene. So that was a famous reaction in AS. Its mechanism was also there. Now, how we used to calculate the bond energy? We used to put the bond energy data from the data booklet. We calculate the total bond energies of the reactant and bond energies of the product. Their difference was called as bond enthalpy. That was a good recall. And now give the heading lattice enthalpy.
Okay, I've copied.
The word lattice is used for ionic compounds. This is a typical word for ionic compounds. Just like in chemistry, the word molecule is especially used for covalent compounds. The word lattice is used for ionic compounds. So after giving the heading, right under it that lattice, the term lattice is used. The term lattice is used for ionic compounds. The term lattice is used for ionic compounds. Now we go for the definition. Definitions are formal and they have to be learned by heart. And now you have to copy the definition.
Okay. I've copied.
So this is the definition of hydration of lattice enthalpy. Now let us again recall that in our AS chemistry, an ionic lattice is a 3D structure, and these are the ions. Look at recall, for the recall purpose, positive ion is relatively small and negative ion is relatively bigger. So this forms the famous ionic lattice of sodium chloride. This is a 3D repeating structure. So ionic lattice is a very strong structure of repeating ions. Look at this compact structure of sodium chloride. How it forms the overall equation is X plus Y minus into solid. For example, sodium ions in gaseous state plus chlorine ions in gaseous state merge to form sodium chloride, especially either state, solid state. You have to copy this screen now.
Okay. I've copied.
Now, lattice enthalpy is exothermic in nature, otherwise lattice won't form. Now,
Yes.
do you remember in AS chemistry, we had a concept that exothermic products are more stable than endothermic products, because if something is lost, if something is formed with energy loss, it will be at a lower energy level. A lattice actually forms when the process is exothermic. Now you have to copy this screen.
Okay. I've copied.
Factors affecting lattice enthalpies. The first is the amount of charge on the ion. Second, ionic separation within the lattice. Two things control the lattice enthalpy: amount of charge on the ion and ionic separation between the lattice. You have to copy now this screen.
Okay. I've copied.
Now quickly discuss this concept. For example, I ask you from physics background that if I have Na plus 1, I have Cl minus 1, they will attract each other. But if I have Mg plus 2 and O minus 2, they will attract each other more strongly. Why magnesium and oxygen will attract each other more strongly? Because they are doubly charged. Because they are doubly charged ions. Second, this is the first point. Second point is there that a positive ion is here and a negative ion is here. In another example, a positive ion in here and the negative ion is here. This is case 1, this is case 2. In case number 2, the ionic attraction is more effective. In case number 2, ionic attraction is more effective because the charges are close to each other. So these are the two important factors we have to consider. Now look at this example. Look at this example, sodium chloride 788. Magnesium oxide is a huge number, around 3,800. Why this is so high? Because magnesium is +2 and oxygen is -2. Now, these are the examples to understand again that the size is a very important factor, and if you have a smaller ion, it will have a greater charge density and it will be able to attract each other ions more effectively. Smaller ions will have a greater attraction for each other because of their higher charge density. Now look at this sodium chloride 788 and potassium chloride 701. Now the point is there that it is the charge density, which determines lattice enthalpy. Now give a new heading, trends in lattice enthalpy.
Okay.
Now, trends in lattice enthalpy, you can look at this diagram. If I ask you to watch this block, you can see there is chlorine down the group 7. So down a group, as the ionic radius increases, lattice enthalpy becomes exothermic. What it means in simple terms, as you go down a group, a lattice becomes weaker. A lattice becomes weaker as we go down the group. But obviously, chemistry is too much formal. You can't write these type of statements in your own words. They won't like it. They won't like bio, and they want that people should at least write the main concept in proper chemistry English. You have to copy this screen.
Okay. I've copied.
Look, as you go down the group, ionic size is increasing. As you go down the group, the ionic size is increasing. Look at this example and the values getting less exothermic.
Yes.
Down the group, lattice enthalpy becomes less exothermic. So it is easier to break a lattice as we go down the group. You have to copy now this screen.
Okay. I've copied.
Magnesium oxide is one of their favorite compounds, and its lattice enthalpy is exceptionally high. Why its lattice enthalpy is so high? Because magnesium and oxygen are doubly charged. You have to copy this statement also.
Okay. I've copied.
semi-qualitative treatment to measure enthalpy change. You have to give this heading.
I've copied.
This is not a formula. This is not a formula to use in any paper. This is actually a semi-qualitative. It is only for understanding that the product of the charges is directly proportional to lattice enthalpy, and the ionic separation is inversely proportional to lattice enthalpy. You have to now copy this screen.
Okay. I've copied.
Now, these are some random values. These are the data values, not asking for any calculation again. This is actually a sample to understand that how it works. Now, I'm comparing sodium chloride and magnesium chloride. Now, you see the charges are +1, -1, so the product will change. The ionic radii are given. So, when you put them in this value, you get one value for sodium chloride and one value for magnesium chloride. For magnesium chloride, the value is much higher, which means it has a stronger ionic lattice. In this way,
Yes.
we can compare ionic lattice. Sodium is +1, bigger, while magnesium is +2 and smaller even. So a small +2 ion will be more effective in this process. When you measure enthalpy change, you have to give a new heading, measurement of enthalpy change.
I've copied.
There are two methods. One is called direct method, which is a topic of paper 5. And second, indirect method, very famous, Hess's law. For ionic compounds in A2, you have to copy that.
Okay. I've copied.
Direct method using a calorimeter. This is called a calorimeter, and we can take the values from this separator. This was in our O-level physics actually, that first you calculate the amount of heat supplied, and then you have to divide it by number of moles to get the enthalpy change. Okay, now give the heading, direct method.
I've copied.
This is actually a topic coming for paper 5. That is an experimental work. we first calculate the amount of heat energy and then we calculate enthalpy change. Do you remember in O-level physics what was the concept of P?
No. C, yeah, specific heat capacity.
Yes, P was specific heat capacity. Now, you have to copy this thing.
Okay. I've copied.
So this is a two-stage process. First, you find Q is equal to MC delta T, and then you find Q upon N, that is the value of delta H. Now, quantitative treatment, Born-Haber cycle, the main topic of this chapter. Born-Haber cycle is the main title topic. In every chapter, there is a title topic. You have to now copy this screen.
Okay. I've copied.
Now, Born-Haber cycle is an application of Hess's law. In AS level, you have done Hess's law. That was mainly for our covalent compounds like methane, organic compounds. But here, Born-Haber cycle is a version of Hess's law, which is especially for ionic compounds. Now you have to copy the introduction.
Okay. I've copied. I've copied.
This is the fundamental thing to remember. Now, there are steps of lattice formation. I am taking it from actually the O level and AS level, how an ionic lattice is formed. Do you remember that when a lattice is formed, we first need a positive ion, then we need a negative ion, then
They
after
will.
that, plus and attract each other.
Yes.
Then the ions come and contact each other, they form a lattice, and this is how a lattice is formed. Both the elements become gaseous. This is the stages to remember. Actually, Born-Haber cycle is a repetition for every compound, for every ionic structure. You need elements become gaseous, which means atomization. One atom loses electron, become a positive ion. second atom gains electron and become a negative ion. The oppositely charged gaseous ions attract each other. They come close until a solid lattice is formed. Now, these steps are necessary to understand that these all are actually energy changes. These all are actually energy changes. Now, the first one means atomization. The second one means electron ionization enthalpy. Third one means electron affinity. Fourth one means lattice formation. The fourth one is the lattice formation. Now these are the 4 stages. But let's do it in the next class because that will be a calculation part. And we are in the middle of the chapter now. So we will inshallah continue this in our next class. Thank you. Bye.
Okay. Thank you.